please. Yeah, thank you very much. Thank you very much for the invitation. It's actually been a while since I gave a talk here. I don't quite remember when when it was, maybe 3 years ago. So. Okay, so I'm going to talk about some homomorphism inequalities in antiferromagnetic graphs. This is joint work with Jae-sung at Kias, who used to be a postdoc of mine at Yonsei University, and Jae-hyun Seo, who's now a PhD student at Yonsei University. Yeah, so let me start with graph homomorphisms. So all of you would probably know what graph homomorphisms are, but let me just quickly recap. So a homomorphism is a vertex map if a vertex map that preserves adjacency. So whenever UV is an edge, its image is also an edge. Yeah, so throughout this talk, I'm going to allow my graph G to have loops. So it doesn't have multiple edges, but it may have loops. Okay, and if you learn about graph homomorphisms, then you would probably see some examples. So graph homomorphisms actually generalizes quite a few important notions in graph theory. So one primary example being the independent set. So independent set, of course, means a set of vertices that contains no edges. So independent sets in the graph H actually has a one-to-one correspondence to the homomorphisms from H to this particular graph with two vertices and one loop and one non-loop edge. So the reason being the pre-image of these vertex here must be an independent set. Yeah, whereas this vertex has no constraint whatsoever. Okay, and another example is a Q coloring, the proper Q coloring. It corresponds to the homomorphisms from H to KQ. Yeah, so these are typical examples of how graph homomorphisms can be used to count something. So if I want to count independent sets, then that corresponds to the number of homomorphisms from H to this guy, and the number of Q colorings is a number of homomorphisms from H to KQ, the complete graph on Q vertices. And once you have a look at these kind of basic examples, another fundamental result in extremal graph theory is a result by Jeff Kahn and Yufei Zhao, saying that any irregular graph H, and then you want to count the homomorphism from H to this guy, which means you're counting the independent sets. So this is a number of homomorphisms, and this is a set of homomorphisms. Okay, and then if you normalize that by 1 over the number of vertices in H, then you need some normalization, because if H is large, then there's lots of independent sets. And then it is always at most the homomorphisms from KDD to the same one, normalized by the same thing, so it should be 1 over 2D. So Jeff Kahn first proved the result for bipartite graphs H, and then Yufei removed these bipartiteness condition after 10 years or so, and hence the theorem. So this is one of the interesting results in extremal theory of graphs, and there are even more. So you can ask some sort of same question for colorings, and you can ask for different target graphs and so on. So there are many such results. So let me just, so for more examples of the same like analogous flavor, I'm gonna refer to Yufei's survey, like extremal results for irregular graphs or something in the American mathematics. So, okay, and there are many results, as I said, but here's one very strong inequality. So here's another theorem by which I'm gonna refer SSSZ. So Ashwin-Sa, Mehtab, Sani, and Cynthia Stoner, and Yufei Zhao. So this is the so-called reverse Sidorenko inequality. So I'm not gonna elaborate on the reasons, but you're gonna see why it's called the reverse Sidorenko inequality if you know what Sidorenko's conjecture is. Okay, so what they proved is given any deregular graph H that is triangle free, you have a very general homomorphism inequality. So if your H is deregular triangle free, and for any graph G, what you have is the inequality that looks like this. Hom HG normalized by the same vector is at most hom KDD G normalized by the same vector. Yeah, so this is inequality. It works for any graph. And the usual Sidorenko's conjecture is about the lower bound for this guy when H is bipartite, but it gives a general upper bound, and hence the name the reverse Sidorenko inequality. Yeah, it's a strong inequality, but of course you can ask more things. So there are two conditions here, one being deregular and the other being triangle free. So the first remark here is that you can actually, it is possible to remove the triangle freeness condition. Sorry, the other, the deregularity condition. Which means I can allow the graph H to be non-regular. So there's a corresponding version of the inequality which makes sense for, it's more complicated of course, but it makes sense for general graph H that is triangle free. So it works basically for any triangle free graph H.
What do you replace KDD by?
Yeah.
So let me just put it this way. So this is a normalized count for H. So if you yeah, so yeah, so this is the inequality. Yeah. So I mean for deregular, the vertex normalization and the exponent and the edge normalization are the same thing, but yeah, for a general thing it's different, and hence you should use the normalized version of homomorphisms, and yeah, this is the version. Okay.
So what's the normalized T?
So THG is the number of homomorphisms divided by the number of vertex maps. So VG to the VH. Yeah. So, and second.
Do you know the loops in this?
Yes. Yeah. So, I mean, it works for graph points. So it doesn't have to be like even like finite graphs. Okay. The second remark is the triangle freeness is absolutely essential in the sense that whenever you have a triangle, whenever you have H that contains a triangle, there exists a counterexample. By counterexample, I mean there exists some G that makes this left-hand side larger, strictly larger than the right-hand side. So whenever your H has a triangle, this theorem doesn't work. Okay, so this is the result.
So is this counterexample complicated?
No, it just, I mean, it's a perturbation. It's an epsilon perturbation from the constant graphon, basically. Yeah. So not really complicated. So there's some girth issue here. So if you perturb your graph around the constant graphon just a little bit, while your perturbation is some sort of balance in the sense that it just makes all these three terms vanish, then the first term you would see from this local perturbation is the shortest cycle. And the shortest cycle being odd length makes, like, shortest cycle being the triangle makes it makes a problem. But odd girth is not a problem apparently, but the shortest cycle being a triangle makes a problem. Yeah. So yeah, I mean you can have a look at this paper, or I also have a note with different constructions, so I can share it with you. Yeah. Okay. Yeah. So let me. Because this is recorded, I should be careful with citings and so on. Yeah. So. Okay. But we were talking about the independent set counts or the Q coloring counts, but I haven't really told you anything about the coloring counts. So here's a theorem by the same group of people in the same paper. So any deregular H. So even without the triangle freeness condition, what you can say about the Q coloring counts is, it's just the same thing. The complete bipartite graph is the maximizer for the Q coloring. Yeah. So for this, you don't really need the triangle freeness condition because you are using very specific target graph. And the same thing happens in the Kan-Zhao theorem. So here's it. So here you're also using very specific target graph. Then you don't really have to worry about this triangle freeness condition. So somehow if you put a right amount of restriction on your G, then it's okay. But in general, it's not okay to put put the triangle, put H without triangle freeness condition.
And the exponent, maybe you put 1/2D over there on the right.
Yes. That's a typo. Thank you. Yes. And let me also remark that this theorem itself actually generalizes a series of results. So for D equals 3, it was done by Ewan Davis, Matthew Jensen, and Will Perkins, and Barnaby Roberts. And if Q is large enough, then this was also done by Yufei. So, this does generalize a series of results, so this is a set of art for the Q colorings, and here we have another theorem about independent set counts. So having seen these examples, you might wonder if there's a common generalization of these results which doesn't require the triangle freeness condition. So here's a conjecture by the same group of people. So their conjecture says that we can actually drop off the triangle freeness condition given any irregular H, but we should put some restriction on the target graph G. And what they're saying is the right amount of condition is the antiferromagnetism. So if your G is antiferromagnetic, then the same inequality should hold. So hom H G is maximized by hom KBD. G with these normalizations. Okay, so what's antiferromagnetic? So as a symmetric matrix, it has eigenvalues, and by antiferromagnetic, this is not defined by me, but defined by statistical physicists. So I don't know anything about ferromagnetism or whatever physics. So that just means that the top eigenvalue lambda 1, of course this being positive, it's lower bounded by the average degree, right? But the others, like lambda 2 up to lambda n, let's say, these are all non-positive. So there's only one positive eigenvalue, then we are saying that the graph is antiferromagnetic. And you can also generalize this notion for a symmetric matrix that has non-negative entries. So this antiferromagnetic, so an edge-weighted graph. So edge-weighted graph with non-negative weights, graph G is also said to be antiferromagnetic. So, I mean, let me just, it's too long, so let me just write AFM. Although AFM would have different meanings, for example, some microscope, atomic force microscope, or even American film market, or even mathematical world. It means asymptotically flat manifold. But yeah, but for today, just for this hour, let me just put AFM for antiferromagnetic graphs. Okay, if it has only one positive eigenvalue, counting multiplicities. And every other eigenvalues are non-positive.
So you allow loops in G, right?
Yes.
So
yeah.
when you take eigenvalue, then you just put 1 on the diagonal if you have a loop?
Yeah. Or other kind of weight on the diagonal is also possible. Yeah. So weighted loops are also possible. Yeah. Okay, and in the full generality, what they prove in the paper is actually you can allow some loops. So let's say you put L loops in your KQ. So that's, yeah. So this also has a nice name, the semi-proper coloring. So it's not really a proper coloring, but if you have loops, then you can have a relaxation of it. So these L loops play the role of repetitive colors. So you can use those colors without any constraints to color your vertices. So yeah, so this is in fact their full result. But of course, it is still kind of far from the full generality because you allow all these non-zero one weights. So for example, here, this guy is a matrix that looks like this, 1, 1, 1, 0, right? And here the KQ corresponds to the matrix with 0 diagonal and all 1 off diagonal, which you can also compute the eigenvalue, and it has only one positive eigenvalue. And if you look at this guy, then this is a KQ with L extra ones in the diagonal. So that's the matrix, which you can also prove that it has only one positive eigenvalue.
Is this antiferromagnetic condition is important? And what I mean is, if it is not antiferromagnetic, then
No. There are. It's not an if and only if conjecture. So, but it captures a lot of important examples in a natural way, and hence the conjecture. Yeah. So this is the conjecture. So we wanted to prove the conjecture, but we didn't really manage to prove it. Like in a full generality, but we actually managed to get something. So yeah, so let me state our theorem. So the conjecture actually holds for the complete graph. So if I ask, so I kind of did a I made a spoiler. So I actually had planned to ask you what's the graph that's furthest from being like triangle free. So then the answer might have been the complete graph, right? So yeah, so this is you don't agree? Okay. Yeah, so this is what we did. So we confirmed the conjecture for H being a complete graph. So which means for any antiferromagnetic G, the following and a deregular, no, it's KD, so it's already deregular. So KD G, when normalized by 1 over D, then this is at most hom K D minus 1, D minus 1, G 1 over 2, D minus 1. Yeah, so this is our inequality. In fact, so here are some couple of remarks. So the first remark being we actually prove something stronger. So what we prove is the inequality that so I'm gonna square this and I'm gonna compare that with a complete bipartite graph minus a perfect matching. So this is the inequality that we are actually proving. So what's this? So it's a complete bipartite graph KDD minus a perfect matching, and hence D minus 1 regular graph. And another way of seeing this is a tensor product of KD with K2, or the bipartization of your complete graph, KD. So what I mean by bipartization, so you can look at this matrix as a bipartite adjacency matrix, right? So you look at you label the columns and rows with different set of vertices, and you put one if they are connected as a bipartite graph. Then this is exactly the complete graph minus a perfect matching, and this is exactly the graph, like yeah, or the tensor product or the double cover has many names. But anyway, once you have this inequality, then you're done because this is bipartite, right? And hence triangle free. So you can make use of this reverse Sidorenko inequality with H being the complete bipartite graph minus a perfect matching. Then you get the right bound. So together with the reverse Sidorenko inequality, what you get is this is at most the complete bipartite D minus 1, D minus 1 G with the correct exponent being 2D minus 1, and it has 2D, so yeah, something like this. Yeah, so I'm done. Yeah, so we are proving this instead of the whole thing. Okay, and second remark is that this inequality actually was conjectured. So there's another conjecture by Yufei, which is about the Q coloring counting. So HKQ is upper bounded, square is upper bounded by the double cover or the tensor product with an edge of H. So this is a conjecture for basically any H, but you can say a deregular H or something. But he conjectured that this works for any H. Sorry, this should be KQ. Yeah, so in a sense, we got inspired by this conjecture and wanted to solve this. If we solve this for any antiferromagnetic G instead of KQ, then together with this inequality, we solve the conjecture. So that was a plan which of course didn't work out. But anyway, this inequality itself confirms this conjecture in a stronger form, although proving this for H being complete graph is not terribly difficult. I mean, you just count the Q colorings of your complete graph that has a very easy closed formula, and it's not too difficult to prove that alone. But what's important here is this is the first result that allows any anti-ferromagnetic graph G instead of a specific one that you can rely on. Okay. So these are some remarks, and what's more interesting about this result is perhaps the method.
Oh, sorry. So by possible to remove the irregularity, does it mean that they prove it is also true, or they conjecture that the irregularity is removable?
For this one,
Or maybe just for everyone?
it depends on the context, but I think in most cases, if you have a reasonable like analog like this, then it should be possible to prove this instead of like it depends on the setting and context. So yeah, but you can always ask some non-regular version of it like this. Yeah, but for that you need a different normalization, which I didn't really want to stick to for this talk.
Do you have also graphon analog for you?
Yes, I mean, as I said, once you pass to this version, then everything pretty much works for graphons. But if you pass to graphons, then the question would be what's the correct correct analog of this antiferromagnetism. It's kind of I haven't really looked into details, but there should be something, but it's tricky because for example, there might be a sequence of non-antiferromagnetic graphs that converges to antiferromagnetic graphon. So yeah, it's kind of tricky to state that in a correct form at the moment, but you can probably work it out. It shouldn't be a big problem. Yes, so any more questions? No? So what's more interesting is perhaps the method itself. So the third remark is our proof uses the emerging theory of Lorentzian polynomials. This is by Peter Brandon and Juni Hao. Okay, so let me talk about Lorentzian polynomials, although I'm quite far from being an expert in this topic. So what's Lorentzian polynomials? So let me start from here. So if your symmetric matrix is antiferromagnetic, I mean, I'm just thinking about the symmetric matrices with non-negative entries and with one positive eigenvalue. Then, so one remark. So antiferromagnetic symmetric matrices. Actually, it has a very special property, allow some sort of hyperbolicity. So what do I mean by hyperbolicity? So it gives a, let's say A is a matrix, and then you have a hyperbolic sort of inequality. So you put U transpose AV, which is a like basically quadratic function that comes from A, and then you just square this, And then this is at least U transpose AU times V transpose AV, or any UV in Rn. So your A is n by n. So why this is called hyperbolicity? I mean, well, for the other extreme, so the ferromagnetic case is actually corresponds to your matrix being positive semi-definite. So if all of your eigenvalues are non-negative, then by some unknown reasons, statistical physicists call it ferromagnetic. So in this ferromagnetic case, if you recall some basic linear algebra, so for the ferromagnetic or the positive semi-definite case, you have this inequality the other way around. So you have U transpose AV, which defines a inner product, right, for the space, the Euclidean space, and then you have this inequality, which is the Cauchy-Schwarz inequality for the inner product space. But here, if you have AFM symmetric matrices, then you have the inequality reversed, which is an interesting part. And the theory of Lorentzian polynomials is to generalize this kind of inequality comes from the eigenvalue to higher orders. So this actually generalizes this part to higher orders. So what do I mean by higher orders? So instead of looking at the matrix itself, I'm going to look at the polynomial, the quadratic polynomial defined by the matrix A. So this is a quadratic polynomial defined by the matrix. And if your A is antiferromagnetic, so let me just put it this way. So if this is antiferromagnetic, then this is degree 2 Lorentzian polynomials. Yeah, so the whole thing actually started off when I went to Juniher's talk at Kias earlier this year in March. So he was talking something about the geometry of these Lorentzian polynomials and so on, and somehow I thought about, I mean, often people like think about some other things during others' talk, right? So what I did during the talk was, well, this kind of sounds familiar. I'm sure I heard about this, and what I kind of memorized is this conjecture by these people, and I started thinking about it. And I also talked to Juni whether he had ever heard about this antiferromagnetism, and he said yes, some physicists call it antiferromagnetic in this lower degree case and so on. So yeah, it all started that way. Anyway, so
are you sure that that is for all U and V, or just for some U and V?
this is for all.
For all.
One.
So this A, if A is identity, then this is like corresponding to this usual our intuition, right?
So for example, if A is say, wait, but by the way, like A could be positive semi-definite, right? So
Why?
what if A is just 1, 0, 0, 0?
This one?
Yeah, this is positive semi-definite.
Yeah, and you have the same terms. Here, u1 v1 squared here, u1 squared v1 squared, right? Yeah, I mean, as far as I checked it, it is. Yeah.
No, positive semi case is
this.
The other thing is right.
Yeah, but his question would have been, what if it's both positive semi-definite and antiferromagnetic, like
And
this?
this is an identity, right?
I mean, identity is positive semi-definite, so you would have this
No,
inequalities.
by identity, I mean that the equality always holds. So
If you have a one random.
So if A is both antiferromagnetic and also positive semi-definite, meaning that ferromagnetic, then the equality
I
always
see.
holds.
Yeah, that's what
Yeah.
you observe.
Yeah. Can I move on? Yeah.
Yeah.
Okay. So to generalize these to higher order polynomials rather than the quadratic ones, you need a couple of things. So definition. So let me just make the definition shorter by making it recursive, although it's less descriptive. So you have a n-variable polynomial with, so this is a polynomial, homogeneous polynomial of degree d, and with non-negative questions. Then this is Lorentzian if the following two conditions hold. So the first one is kind of clear. So you take a partial derivative with one of the variables. So for any I, 1 up to n, you take the partial derivative of f, then you have a lower degree homogeneous polynomial of degree d minus 1, right? And this is Lorentzian. So this is a part when I use the recursive definition. But you need one more condition to satisfy. So this is not quite enough to make all the theory works. So the second condition is the support. So here the support of f is not really support of f as a function, but the support of f as, so if I collect all the monomials that actually appear. So if I have x1 and x2 as a monomial, then I'm gonna say that this 1, 1, 0, 0, 0, the corresponding vector is in the support. So support basically is a collection of the monomials that are appearing in the polynomial. And as a multiset, so this is a multiset because I can also encode the degree like this. So if I have x1 squared x2, then I put 2, 1, 0, 0, 0, which is a multiset using 1 twice and 2 once, and there's nothing else. Okay? And the support of f is M convex, which doesn't mean anything at the moment. But here M convex just means that this is a polymatroid. So I'm not going to define what matroid is at the moment because of the time limit, but it's a multiset generalization of a matroid. So as a multiset, it allows the standard base exchange axioms, blah, 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 and hence it defines a polymatroid. Then this is conditioned. The M convexity is the like support of f being polymatroid. So there are two conditions to satisfy. So one being this is the lower degree one, the partial derivative being Lorentzian, and the other being the support satisfies some sort of combinatorial condition. Then you say that your degree d homogeneous polynomial is Lorentzian. Okay, so this at first glance looks quite hard to satisfy, but there are quite a few interesting examples, and the examples are like new examples are found in a real-time basis, and hence the theory makes it quite interesting. But once I have this Lorentzian property, then what's good about this is maybe I should have used something. Okay, okay, I can keep this part. Okay, so as an application, so this is a theorem by Peter Brandon and Junhee Ha. So if f is Lorentzian, then what we have is this large f sub f. This function is a multivariate function that is defined by v1, v2 up to vd, and you take the 1 over d factorial lambda 1, lambda 2 up to lambda d of f x1, v1, x2, v2, xd, vd. So here v1 up to vd is a vector, whereas x1 up to xd is just a variable, the scalar. And you put these vector into your f, so these are in Rn. And then you take the partial derivative, which is basically a multilinear generalization of this polynomial here. So, I mean, to state something like this, you need a multilinear generalization of your polynomial. So you should allow something like this out of a quadratic polynomial. And this is somehow the mysterious way of doing this. You have any questions?
So it's it's a multivariate polynomial still, right?
Yes, yes. So you put this vector, the linear combination of vectors, as an input.
Ah, yes.
Yeah, and you look at the what? Yeah, I mean you just expand it out by using x1 up to xd, and then you look at the quotient of x1 up to xd in that particular polynomial that is expanded out, and that corresponds.
Yeah, I understand now. Thank you.
Yeah, so in geometric setting it could be a mixed volume, or in the discrete setting it could also be a mixed discriminant, and so on. Then this function has low concavity, or the Alexandrov-Fenchel inequality. So what do I mean by this? So Alexandrov-Fenchel inequality comes from convex geometry. Is, let's say, so I have a d variable function here, and then I square it, and then I look at those functions that repeats one twice and move on to the third one, and I repeat the second one twice and move on to the third one. And then if I compare these two, then it comes as a generalization of these inequalities here. So this is the, when we put this f, large f sub f as a mixed volume, then it recaps the classical Alexandrov-Fenchel inequality in convex geometry. So this is a consequence. So we want to use this in our setting. So now the question is, how do we use this theory in our context properly? So the answer is as follows. So let the polynomial h of kd, so I'm using n variables, so I should define n variables. So here, this is a graph on the vertex at the integers 1 up to n, and then I'm gonna do this. So given a homomorphism from kd to g, what I'm gonna do is to count the inverse image. So how many times that I used the vertex number 1, and how many times did I use the vertex number 2, and so on. And
cardinality. Right?
yeah, yes, I put these on the exponent. Yeah, so if you are working on a weighted graph, then you should put a corresponding weight of your homomorphism phi. So that's how you define your polynomial. And although it looks quite complicated, it does have some context. So if you look at h of x1 xq of kq, then this is what's called the chromatic symmetric polynomial. So this was defined by Richard Stanley in 80s or something. Chromatic symmetric polynomial. And I mean, these kind of polynomials actually appears in lots of different contexts. For example, if you use K2, let's say, then you get a Lagrangian and yeah, and so on. So yeah, these kind of polynomials appear in various contexts, and our theorem is actually this polynomial is Lorentzian if your G is antiferromagnetic. So this gives another interesting family of Lorentzian polynomials that were unknown. So it adds more examples to the theory with an interesting application. Okay, so now the question is, we proved that this is Lorentzian. And so how much time do I have? Maybe 10?
More than 10, but anyway.
Okay.
Sorry, I missed the question. So what's the weight of phi?
So when your graph is weighted, then each of your homomorphism receives the corresponding weight. So it multiplies all the edge weight that is used in the map. So that's the weight of the yeah, homomorphism. Yeah, so that's yeah. Yes, so if I have more time, then let me just give a sketch proof. So how do we prove this theorem? So you can just recall that there were two things to check. One, you should take a partial derivative. So yeah, you should take a partial derivative. And the other thing is M convex. So first sketch. First, to check if the partial derivative is Lorentzian, it actually, so let me just put it this way. So if I take kd plus 1 and look at the partial derivative with ith variable, then actually this corresponds to hkd in G induced on the neighborhood, so neighborhood of I. So what do I mean? So here what I'm actually counting is a kd plus 1 homomorphism that uses ith vertex. Otherwise it doesn't contain xi, so it vanishes. So here I'm basically counting those homomorphisms of kd plus 1 that uses ith vertex in any kind of ways. So, and then I look at which corresponds to a copy of kd minus 1 here in the neighbor set of ith vertex.
Why t minus 1? Is
Sorry, d. Yeah, so I was, yeah, thanks for that correction. Yeah. So yeah, this is more like an observation. So you can just work it out, and you can easily prove that this works. And the second one is to check the M convexity. So for M convexity, you somehow have to prove that the homomorphisms form a polymatroid. But that needs some work. So to prove M convexity, you need a proposition saying that any antiferromagnetic graph G, we look at the support of it, which means I just look at those entries that are non-zero and turn it into 1. Right? So I look at the support of G, which is a 0, 1, and again antiferromagnetic. This is not so easy to see, but it is true. So, and then this 0, 1 antiferromagnetic matrix, or a graph, has a structural characterization. So which is the following. So G must be, so if G has no isolated vertices, because isolated vertices doesn't do anything to your homomorphisms. So no isolated vertices, then your G is basically a complete R-partite as a graph. Complete R-partite plus apex loops. So by apex loops, I mean those looped vertices must be connected to all the vertices, including itself. So there's a looped vertices that are connected to one another, which connects to all the other vertices, and here you have a complete multipartite graph. So this is a full characterization of 0, 1 antiferromagnetic graphs that you can actually work out.
So what does this, for every AFMG, such that support?
No, it's not a, so given this, I'm gonna turn this to a 0, 1, and then the support is actually complete R-partite plus apex vertices.
So how do you turn it? So the G is a vertex weighted graph?
Yeah, no, edge weighted graph.
Edge weighted.
Yeah, and you turn every non-zero weight to 1.
Oh, okay.
Yeah, you just look at the support, basically. And then it's a 0, 1 matrix, and it is enough to argue your M convexity in the support, because M convexity itself has nothing to do with the weights. It's a purely combinatorial notion whether this whether this particular homomorphism exists or not. So we can always pass to its support
So
to.
this is if and only if.
Yes, yeah. So this is a full characterization. So, I mean, this, what I mean is this is if and only if, I mean, let's say G being this is, if and only if G being 0, 1 antiferromagnetic matrix.
I guess this is also used in the first part, because then any induced subplot with G also has that.
For this, I actually cheated a bit. So for this, for the weighted setting, you should use the weights. So you somehow have to pass the edge weight to the vertices somehow. So I kind of cheated here by like implicitly assuming G is 0, 1, sort of. But to make this rigorous, you should pass the weight to the vertices, which is not really exactly these, but somehow you should make a more judicious choice for this guy. Yeah. And of course, all the induced subgraphs of antiferromagnetic matrices is again antiferromagnetic because of the Cauchy interlacing formula. Yeah. Okay. So where are we? So we kind of gave a proof sketch, and for the rest, let me sketch how we use it. So now the question is, what's this in our setting? So here, what's great about the theory of Lorentzian polynomials is I can make use of where's that? I can make use of this Alexandrov-Fenchel inequality by using this multilinear generalization. So in this case, this corresponds to what we call the H volume in G, or KD volume in G. So we have a same multilinear generalization of our HKD, which is a polynomial in n variables. And what it gives is actually some restricted homomorphism count. So here we need some vectors as an input. So we need v1 up to vd as an input. So v1 up to vd, so I'm not going to define that very precise, but let me just give you some idea on what happens. So what's this which corresponds to the f sub f? If I put some indicator vectors, so these are meant to be vectors in Rn. But if I only restrict myself onto a 0, 1 vector, then this v1 up to vd, if I look at these as indicators of some vertex set, let's say a1 up to ad, then what it does in this particular case is you just count those homomorphisms that maps the first vertex in KD to A1, second vertex to A2, and so on. I mean, these are this notion actually appears in various contexts. Like, for example, in regularity lemma and counting lemma, you also count things in these part-type constructions and so on, and it's some sort of linear relaxation of this restricted homomorphism counting. And what we can prove is this kind of inequality also holds for our KD volume in any antiferromagnetic G, and that's what we are using. So for -2 minutes, maybe I can I can just briefly sketch what's going on. So what I want to prove is comparing 2 copies of KD to vertex disjoint union of KD versus 1 copy of KD times K2. So this is what we wanted to prove. And the proof is, of course, by induction on D. And by induction on D, what I have is the following. So on one hand, so I want to count a red copy of KD, which means I only use red vertices. So suppose I have some red vertices spread around, and I want to also count yellow copy of KD, and I want to compare this with KD times K2 that crosses between red and yellow. So this is the inequality that I want to prove. And yeah, so for the lower degree case, let's say D equals 2, this exactly corresponds to the hyperbolicity. So this exactly corresponds to this inequality over here. And for the higher degree, what I'm going to do is we fix 2 vertices, let's say. So one being red and one being yellow. And we look at the neighbors of it. And here I want to find a copy of KD. And here I want to find a copy of red KD. And then if I just replace these yellow and red copies by induction, then what I get is a red copy here, there, and here yellow, red, and here I have a copy of KD times K2, and here I have another vertex that is adjacent to all the vertices here, and I have another vertex here that's adjacent to this, and this recaps the colored version of KD plus 1 times K2. What remains is I should maintain the induction hypothesis, right? So what I have to prove is this inequality over here, which uses red vertices and KD and yellow vertex and KD. So this is overall a red copy of KD plus 1, yellow copy of KD plus 1. And that's where this Alexandrov-Bentel inequality is used. So this is where we use this, where is that? Yeah, where we use this inequality. If you think about all this indicator form for a while, then this is exactly the form that we are using. And yeah, so this is a very brief sketch of the proof. So let me just wrap up with some open questions. So of course I want to see more applications of the theory, but here are some, and the solution for this conjecture by 4 people, Sauni, Stoner, and Zhao. But another question you can ask is what polynomials of this type is being Lorentzian for various choices of G. So our conjecture is that if you want this guy to be Lorentzian for any antiferromagnetic G, then the complete graph that we found is the only answer. One that gives Lorentzian KD. Yeah, so let me just put it differently. HKD is the only one that gives for any antiferromagnetic G. But you can also ask the same question for other graphs G. So there are some results there. So if you want to look at the independent set count, then this is a quadratic polynomial because there are only 2 vertices here. Then a result by Chudovsky and Seymour. So it's not really stated in that way. What they're proving is a real rootedness of independence polynomial. But if you have real rootedness, then you have low concavity, and then you have this Lorentzian property. So what they proved is the independence polynomial is real rooted whenever it is claw-free. So which means for claw-free H, your polynomial x1, x2, this is Lorentzian. So this can be phrased in that way. And there's another result by, so when G is KQ, then it corresponds to the chromatic symmetric polynomial. So you are basically asking when the chromatic symmetric polynomial is Lorentzian. Then what you have is the result by mathrm, Morales, and Sellover. And what they conjectured, is if you have unit interval graph, which is an intersection graph of unit intervals, then this chromatic symmetric polynomial h of KQ is Lorentzian. And they proved a particular case for the abelian case they call, but it takes a bit of effort to understand what that means because it is stated in terms of the deep path and some algebraic combinatorial notions. Yeah, so it would be interesting to see what kind of examples that we can get for the Lorentzian polynomials, and of course some other conjectures and so on. Yeah, so this is it. Thanks.
Thank you. Any questions?
So I just confused. So about the result by Chudovsky and Seymour, so you say this is real rootedness, so is it implies just Lorentzian?
Yes. Yeah. So real rootedness implies the log concavity, and in 2 variables log concavity of the questions, it's just it gives Lorentzian property.
So if your conjecture is true, that means at least this approach wouldn't work for the whole conjecture, right?
That's true. Yeah, that's true. I mean, even if we have the Lorentzian property for any other H, here we are relying on the very specific structure information of complete graphs. So yeah, I'm not so sure that it would work. Yeah, for example, even if you use some of their results, I'm not so sure that you can work something out like this.
So the Lorentzian is used at that step at the AF inequality.
Yes. Yeah, it's. I mean, I tried quite. I mean, we tried quite hard to push this to some other directions, but it's quite rigid, I would say, at the moment at least.
So have you ever thought when H is C4?
H is C4. Yeah. I mean, for these small graphs, we ran some computer search, and yeah, there are some antiferromagnetic G that gives a counterexample, non-Lorentzian polynomials. So yeah, for small graphs, we all checked. That's yeah. So somehow, for these two conditions, I erased the second, but I mean, this is somewhat harder. So M convexity, so we have another theorem saying that it is enough to check the M convexity for G equals KQ. Yeah. I mean, if we want to check M convexity for any antiferromagnetic graph, then it is actually enough to check for KQ, because essentially looped vertex, which is an apex, doesn't harm anything about M convexity. So we basically reduce it down to a blown up KQ with different sizes, and yeah, this complete R part type essentially yeah, boils down to the KQ. So for M convexity, their problem is as same as ours, but the differentiation part is somehow trickier to satisfy, and hence we conjecture that this obvious sort of way is the only way to guarantee this differentiation to work.
Right. Any other questions? Okay, if not, let's thank the speaker.